In today's lesson, we will be finding the area between curves, and these will all be with respect to x. So in a later lesson, we'll be doing this with respect to the y-axis. So the main idea of this, I think you'll find, is pretty easy. We'll have some challenging questions, of course, but the area between two curves is simply on an interval from a to b, is we're taking the integral of f of x minus g of x. But the trick is you're always looking, that first function has to be the higher function when you're on this interval. So f of x has to be greater than g of x. So for an example is, let's say, just kind of do this little sketch here. Let's say this is f of x, and let's get a different color. Let's say g of x does something like this. Notice how, well, first we would have to know if this was the area here between the curves. To know the interval, we would have to know these points of intersection. So sometimes you're given the interval, but sometimes you have to find the points of intersection to create your interval A and B. And then notice how on this graph, f is above g. So therefore, we do the f of x first minus g of x. So for our first example, we are going to find the area that is bounded between these two curves, or these two equations. Okay, so just to kind of give you a visual, okay, so this first one is a parabola, so we know it's going to look like this. And then here we have a linear function that's going to cut through like this, and we're going to be finding this area. So we have to know the points of intersection. Well, the points of intersection are when these two functions are equal to each other. And then on this interval, as you can see, the linear function is above. Linear function here is above. So we're going to have, this is our f of x, and this is our g of x. So let's first find those points of intersection. So let's set x squared minus 4x minus 5 equal to 2x minus 5. So to solve this, we've got this quadratic, so let's move everything to the left. So we'll have x squared minus the 2x, so it goes to minus 6x, add 5, cancel out, so equals to 0. Let's factor. So intersection points will be at x equals 0 and at x equals 6. So we will be finding, to find this area, we'll have the integral from 0 to 6. And then, so if it's f of x minus g of x, let's think about that. That's going to be the 2x minus 5 minus x squared minus 4x minus 5. So if we simplify that, we'll have negative x squared, 2x, and then that's going to go to plus 4x, so plus 6x, and negative 5 minus negative 5, so they will cancel out. So let's evaluate this definite integral. So antiderivative, negative x to the third over 3 plus 6x squared over 2, and evaluate it from 0 to 6. Okay, so let's plug in the 6, negative 6 to the third over 3, plus, we can simplify that down to 3, and then 6 squared, and then subtract. Okay, when you plug in 0, you're just going to get 0. So really all we have to do is evaluate this. You'll get negative 216 thirds plus 6 squared is 36 times 3 is 108. And oh, that ends up being negative 72 plus 108. So our answer is 36. And that would be units squared because we're finding area. So we just found, so 36 is the area bounded by those two curves. Okay, so this next example, we're not going to fully evaluate, but we are going to set up the integral. So what we actually have four functions here, four equations. So we've got square root of x, that's this one here. And then x minus 3, there's your linear one there. X equals 0, so we're including the y-axis. And then y equals negative 2, which is this right here. So the area that bounds them all together is this. So on the left, we have this clear starting point. So it's not like we need to find these intersection points because it's starting at 0. But notice how, what's happening here. This is bounded, let's see, that square root function and that y equals negative 2. Those two functions, here's the area between those two functions. And then it switches. This is now the square root function and then the linear function. So the area between those two. And you can clearly see here that this is intersects right at 1. And then, but we don't know where this intersects. So that would intersect when the square root of x is equal to x minus 3. So for this, I'm actually going to plug these in to my graphing calculator in my y1, y2 graph, find the intersection point. And they are actually going to intersect at the point we're going to call it A, is 5.302775.6. So that is this point right here. So let's now write this integral. So we're going to have to find the sum from 0 to 1. So of this red, 0 to 1. And that is, let's see, what's the upper function? The upper function, this f of x, is the square root function. And the lower one, g of x, is this negative 2. So square root of x minus negative 2. And now, let's do this blue section. We have from 1 to point A, which we've defined as that intersection point. And let's see, f of x is still that square root function. But now we're subtracting that linear function, which is x minus 3. So we can clean this up a little bit. 0 to 1, that's the square root of x plus 2. Plus from 1 to point A, and that would be the square root of x minus x plus 3. So we're not going to fully evaluate this, but just understanding how to set it up. And this last example, a little bit different. We have, so here's the square root of x, and then we have negative square root of x, and then we have x equals 3. So the area bounded by those three equations, but this time we're not finding that area. We are going to find the line, a vertical line, so x equals a number that divides this into two equal parts. So is it here? Is it here? Here. Trying to find that vertical line that would make the two areas equal. Obviously, if we had the horizontal line, we would know, oh, well, that's going to cut it in half equally. But what we want is to try to figure out that vertical line. to make this equal to this. So we have to find that x value. So let's first set up the integral here. So we're finding essentially the area between these two curves. And we've got, so think of this as our f of x, and this is our g of x. So what we want to do is from 0 to what x value does, let's see, the square root of x minus negative square root of x. When is that equal to, when we have that k value to that far right, 3, of the same area, like the same two functions, square root of x minus negative square root of x. And to clean that up a little bit, 0 to k, and that would go to 2 square roots of x. When is that equal to, from k to 3 of 2 square roots of x? Well, let's take the antiderivatives. Remember, square root of x is the same as x to 1/2. So on the left, we have 2 times x to the 3/2 over 3/2, and we have to evaluate that from 0 to k. And then we've got the same thing on the right, 2x to the 3/2 over 3/2, but we're evaluating it from k to 3. So if we're doing 2 divided by 3/2, that's the same as 2 times 2/3, so that's going to be 4/3. So on the left, 4/3, let's plug in k. 4/3 k to the power of 3/2 minus, plug in 0, that's just going to be 0. When is that equal to 4/3 plug in 3 times 3 to the power of 3/2 minus, now plug in k, 4/3 k to the power of 3/2. And our goal is to solve for k. So let's get our k onto one side. So I'm going to add this term to the other side. So that would give me 8/3 k to the power of 3/2 equals 4/3. Let's see if I can simplify this a little bit. So that's the square root of 3 to the third, 27. So the square root of 27. And then at this point, we can use our calculator. You could use your y equals and like find intersection points, but algebraically, we can just evaluate this, multiply both sides by this reciprocal, and then we can raise both sides to the reciprocal power. So we will get that k equals about, we'll round it, 1.8898. Okay, so what did we just find? That k value, let's go back up here. That is, so right here, x equals that k value, 1.8898. So let's graph that. 1.8. We can estimate that about right here. If you draw that vertical line, that is the line that would make this area equal to this area. And there we have the end of the video. So there's your video on finding the area between two curves. And this is going to be the theme of the rest of this unit. So good luck.